Hello, welcome all. Good afternoon. So this is the ninth tutorial of the day. It's an uncertainty quantification. This is completely hands-on tutorials hosted by our colleagues from IBM, Twitter, Microsoft. I think this is going to be a very interesting session. So before we start, couple of things for the attendees. If you have any questions for the speakers, please post your questions in the Q&A box. So there is a button at the bottom right. You can see that there's a Q&A. This is the box meant for the questions which you want to ask to the speakers, and we will collect all the questions and keep that towards the end, so that after the presentation, after the hands-on demo, we'll take one-on-one and then we'll try to figure it out. So without wasting further time, so let's invite our colleague Prasanna from IBM. Prasanna, the floor is all yours. So please take it
Okay, thank you. Thanks,
confidently.
Chiranjeev.
Yeah.
Yep, you can hear me, right?
Yes, can hear you.
Okay. Okay, great. Yeah, so thanks everyone for joining. So I'm Prasanna, and my colleagues would not join in person here, I mean live. So we have a pre-recording, and that I'll play right now. And please feel free to ask questions and interrupt, and I will be available live in the end to to answer questions as well. And thanks again for joining, and let me play the video now. Hey everyone, and welcome to this tutorial on uncertainty quantification 360. And this tutorial will be presented by myself, Prasanna Satyagiri, and my colleagues Soumya Ghosh and Jerry Navratil from IBM Research. And before we get started, a few useful links. This is a link to our Slack community. You can go to this link and get added to the workspace, and the relevant channel is UQ360. There's a separate channel for users and developers, and feel free to join any of those so that you can interact with other users and developers for any other questions or future improvements and so on. And these are some other useful links. The first link is the link to the interactive web experience. The second one is a GitHub link, and the third one is a PyPy link. So yeah, so this is a rough agenda for this tutorial. I will start with a brief introduction to the topic, the uncertainty quantification, what we mean by that, and a gentle introduction to the toolkit, followed by an interactive web experience demo. And after that, I'll hand it over to my colleagues, Soumya and Jiri, to do a deep dive into specific uncertainty quantification algorithms and metrics. All right. So yeah, let's get started. So yeah, the what question, right? So what do we mean by uncertainty quantification in AI? If we were to define it in simple terms, it's essentially the ability for an AI model to say, I'm unsure, right? And just to give an example, let's say we have an AI system that's deployed in a hospital setting, and it takes a patient X-ray and it tries to predict the disease state, right? For example, presence of pneumonia or not. And what we want such a system to be really useful and actionable is that it should provide us not just the best guess, but also some measure of confidence or some uncertainty estimate, right? So how does that look like, right? For example, in this categorical case where there are only two classes, it will give us a score associated with each prediction, right? So presence of pneumonia, in this case, is 0.45, and no pneumonia is 0.55. As you can see, the model is not really confident, right? And when a consumer of these decisions, let's say a doctor, has access to these confidence scores, they can intervene and reject the model's predictions and thus avoid any harms that might be arising from poor predictions from the model, right? So, for example, in this case, the doctor might order more tests, or gather more information, or refer the patient to an expert, and so on. So, having access to uncertainty measurements or confidence measurements adds a layer of safety, right? And it really enables human AI collaboration. And I mean, we can look at some other use cases as well. This is just for illustration purpose, right? So there could be a lot of different ways in which you can use uncertainties to improve your understanding of the model and thus build some sort of trust in the model predictions. And in this way, this example that I have here is a way of looking into the model's mechanisms, right? How it is coming to a particular prediction. And what we could do in this particular setup is we are asking a question: what should change in the input in a particular instance such that the model becomes more confident or less confident, right? And that tells us what the model considers as important to arrive at a particular prediction. And based on this information, then we can go ahead and ask the domain experts, does this match their beliefs and their understanding of how a particular prediction should be arrived upon, right? And this could be an interesting way to understand what the model considers as important. Right. On the other side, we can directly use uncertainties as a way to improve our models. Right? Active learning is a well-known paradigm which uses uncertainty to do this. And the way it works is you train a model on some data set that you have access to in the beginning, and then you compute the uncertainties of the model in different input regions. And wherever the uncertainty is high, you will aim to collect more samples from that region, right? So this is an efficient way of collecting more training data wherever we think the model is not confident or not working as intended. We can go ahead and collect data and improve the model, right? So and the question is, how can we rely? We have access to a model and gives us some uncertainty estimates. Are these uncertainties reliable, right? And typically, we don't have access to ground truth uncertainties. So we need to use some sort of surrogate metric. And calibration is one popular approach to do this, right? And to understand calibration, we can look at reliability plot. This is one way of expressing the calibration of the model. And it's a simple concept. If you look at the model confidences, let's say, and to understand this in a very simple way, let's consider all the instances where the model has a confidence of 0.08, right? And a feature of a well-calibrated model will be that for all the instances where the model had confidence score of 0.8, the accuracy of the model will also be 0.8, right? So if it varies, if it is different from 0.8, then we would say the model is, if the accuracy is larger, then we'll say the model is underconfident. If the accuracy is lower, we would think that the model is overconfident, right? And using our toolkit, we can also plot this reliability diagram for a group, right? And these groups may be based on demographics or some other group feature, right, that you consider as important. And you can see in this particular example that the well-calibrated model, based on the definition, this plot should be close to the diagonal line. And you can see that one group, the orange group, the calibration curve is much closer to the diagonal line, whereas to the blue group, it kind of drops off, right? So the model is much more overconfident here in this case for the blue group. And this is helpful to diagnose what might be wrong with the calibration of the model, right? And another way to express calibration or to look at the calibration of a model is to look at these error versus coverage plots, right? And you can replace error with precision also, or any other risk metric that you care about, right? And coverage here corresponds to how many samples did you accept or reject. And the idea in this kind of approach is to reject samples where the model has high uncertainty, right? And as you reject samples, your coverage reduces. And the expectation is that as you decrease coverage, as you accept only highly confident predictions from the model, the error rate should go down, right? And that's the trade-off you're willing to accept. But if you can see that in a simple baseline model where we don't think about different groups, it's possible that the error of one particular group reduces, but the other group, the error might actually go up. So we need to think about these issues as well. And this is one of the diagnostics tool we can use to evaluate how good the uncertainties of the models are. All right. So yeah, I mean, if you look at that was classification. Now, if you look at the regression case, it might be even easier to understand this notion of calibration, right? So to illustrate, I have this example here. So let's say we have 4 test instances and we have 2 different models. And in this plot, the blue solid line is the ground truth, right? And the green dots, green circles are the mean estimates. You can see in both cases that the mean estimates are quite close. So in terms of the mean estimate, the models are performing quite similar. But if you look at the prediction intervals of the model, in one case, the prediction intervals are much larger. And this is reflected in this metric called mean prediction interval width. For this model, it's around 40. For this model, it's around 15. So this model, on an average, has less uncertainty around its prediction. But the other important factor to look at is, do these prediction intervals really cover the ground truth or not, right? And you can see in this case, out of the 4 instances, 3 instances, we have prediction intervals where the ground truth is actually within those prediction intervals. So this is a desired property. And in this case, the PICP score, the prediction interval coverage probability, is 3 or 4 or 0.75. Whereas in this case, it's just 1, right? So it's 1 over 4, the PICP score is 0.25. So on an average, there is less uncertainty in the predictions here, but it's not actually covering the ground truth. So these are less reliable compared to this. So there is a trade-off between how much uncertainty we can accept and what is the actual coverage probability of these prediction intervals. And both are kind of important, and it's important to consider the trade-off in many cases. All right. So now, like, why do we see this behavior? Why uncertainties might be unreliable, right? And there could be quite a number of reasons why uncertainties could be unreliable. But most often the reason is that the models that we have, they don't capture all sources of uncertainty, right? And the most of the times when we use a standard machine learning models, we end up capturing data uncertainty in most cases, which is the natural variability in the data between the input and output variables. But we often end up missing model uncertainty, which corresponds to detecting the regions in which the model has not been trained on, right? And wherever the model has not been trained on, we expect the uncertainty to be high. So that brings me to this next slide, right? So what we really need is a lot of different diverse algorithms which can capture different sources of uncertainty, right? They should capture data uncertainty, they should capture model uncertainty, and there could be other sources of uncertainty such as model misspecification and so on. And each of these algorithms will have some trade-off in terms of their efficiency, their computational complexity, and so on. So each application might, we end up choosing a different algorithm based on our constraints and what our needs are. Right? And so these are all the algorithms that are there in the toolkit, apart from intrinsic algorithms, which are basically when you don't have a model trained, you are training something from scratch and you have choice of these algorithms. But there are also algorithms which act in a post hoc manner, right? So you already have pre-trained a model, and then you want to improve its uncertainty, either through some sort of recalibration, or let's assume that your model doesn't give any uncertainty at all, then you can have some other ways, such as meta models, which Jerry will talk a little bit more. And then infinitesimal jackknife is an interesting approach as well, which could be applicable in a post hoc manner. All right. So, and the other important aspect is you have a model, it can give you uncertainties, you make sure that it's accurate, well calibrated. But we also need to communicate this uncertainty to decision makers, right? And here, I think we need to be careful in the way we convey the uncertain information. And so that it's digestible and actionable to the end user. And the toolkit has some of the functionality in the toolkit is geared towards this. Okay, so yeah, so we really need a sort of a workflow for uncertainty quantification, right? So I think that's kind of the gist that I would want to convey, and that's what the toolkit is geared towards, right? Just to go through this workflow, you might have a model that you already trained. In this case, you could either want to improve or estimate how good the model uncertainties are. You can use some sort of post hoc methods to extract uncertainty. And then you could improve the model uncertainty. And finally, you could communicate the uncertainty to the end user. And if you don't have a model already trained, you could pick one of the intrinsic QQ algorithms and perform this loop, right? Evaluate how good those uncertainties are. If you are not satisfied with the uncertainty quality, you improve the quality using one of the post hoc methods, and you repeat this loop. And once you're satisfied with the uncertainty quality, then you can choose how you want to communicate the uncertainty to the user. And the toolkit provides different blocks and different functionalities for each of these steps. Okay, so yeah, so that was a quick introduction and motivation for the toolkit. Now let me jump to the interactive web experience to give a motivating example and walk you through the things that we have in the toolkit in a little bit more detail. Let me switch the screen. All right, so this is the link to the interactive web experience. It's uq360.mybluemix.net. And let's just jump into this web demo. Right? So this is a simple example to show how uncertainties can be extracted and used and communicated, right? So let's assume there are two personas, a data scientist and a house seller. And the data scientist is building a model, extracting uncertainty, and the house seller is consuming those uncertainties and using them in some decision-making process, right? So in this case, we are building a house prediction model, and the data scientist is using a bunch of features. For illustration purposes, we use only two features, let's say number of rooms and crime rate to begin with. And the house seller would want an estimate of the house as well as some sort of uncertainty around that estimate. Right? And again, this is what the workflow would look like. The data scientist will choose a model and uncertainty estimation method, evaluate the uncertainty estimation quality and improve it if it is not up to the mark, and also use the uncertainty as a guide to improve the model, and finally communicate to the end user. Right? So let's look at each of these steps. So in this case, we assume that the data scientist is building a new model from scratch, and they want both model uncertainty and data uncertainty. And the data set is relatively small and easy to handle. So they end up picking Gaussian processes as the uncertainty estimation method. And the house seller, the end user, requires that the prediction intervals have a PICP score, or the coverage probability, of 95%, right? So they expect that the prediction intervals contain the ground truth 95% of the time. That's the expectation, right? So now the data scientist builds the model. The next step is to evaluate and see how good the model's PICP scores are, right? And using the tools in the library, you can actually compute the PICP score for the whole data set, but you can also visualize it by different feature values, right? So for example, here, the data scientist was using number of rooms and crime rate per capita as two features. And they can plot the PICP score for each room. And you can see overall the BICP score is 0.83, which is still less than the desired score of 0.95. The mean prediction interval is around 311. Um, and you can see that as the number of rooms increases, the BICP scores goes down. So you can conclude from this that the model becomes unreliable for houses which has large number of rooms, right? And one way to patch this up in a post hoc manner is to do some sort of recalibration on a validation set. And the data scientist here uses uncertainty characteristic curve. The jury will talk a little bit more in the later part of the tutorial. And by using this recalibration scheme, you can actually increase the prediction interval width such that they cover the ground truth, right? So it will actually reflect the model's uncertainty more honestly. And once you do this recalibration, you see that the PICP score has gone up considerably. It's above the desired level of 0.95, and which is also true for most number of rooms now. And the price that we had to pay is that the average uncertainty has now increased, right? So this is one way in which they can improve the uncertainty estimation. But as we see that this comes at the cost of increased uncertainty, right? Mm. A more better way would be to improve the model by collecting more data, right? And for this, the uncertainty could be decomposed into the model uncertainty and data uncertainty. I wouldn't go into the details of the process here, but essentially, the idea is to use the uncertainty as a guide and then collect more samples in regions where the model is lacking, and then retrain the model. And that's what the data scientist does here. And the end product would be that the uncertainty is much lower, the PICP is much higher, right? So let's go back to our workflow and let's look at the final step, right? When the data scientist is handing over the model to the decision maker and providing a way to visualize these uncertainties. And there could be different ways in which we can communicate uncertainties. The simplest would be to just verbally communicate the prediction interval, the 95% prediction interval, right? So the mean estimate and the plus or minus are quantiles. Uh, in some cases, it might be useful to provide the whole distribution so that the end user is aware of the different range of possible values and the probability associated with that. This might be hard to digest, so there are much um, easier to understand plots such as quantile dot plots, which shows the relative odds, and this might be much useful for the end user. So the toolkit has these functionalities as well. Okay, so that sort of concludes this web demo, which that there is a notebook which goes through this example in a much more detailed manner, where we actually see code associated with all these plots. I would encourage you to take a look at that. And before we move on to the deep dives, I can just go over this web page a little bit more and tell you what all is here. So we have this page, which gives the overview of the different functionalities. This is something that I talked about. This might be useful to go over. It also describes things that I mentioned in terms of different kinds of uncertainties, all the different algorithms that are in there, and the different metrics that are in the toolkit. A small guide in terms of how to use the uncertainties. And these have also has links to other resources on this web page, right? So we have a mini guide on how to use different algorithms, in what cases they may be applicable. And we have a similar guide on metrics. And we also have a detailed guide on communication methods. So I would highly encourage you to take a look at this as well. And it's also describes the regression and classification cases in much more detail. Um, and then it has a glossary, which formally describes the different terms that I've been using. So these are links to some of our papers and other relevant papers. And these links will take you to a lot of different code examples that we have for the toolkit. And uh, finally, let me go back to the main page here. And the API docs can be found here. And this will be the most up-to-date link for any documentation, and you can find more details and references for all the different algorithms. And finally, let me just jump to the GitHub repo, right? And this has instructions on how to set the library up and um, how to start using the toolkit, right? So for the next part, feel free to run this in parallel, install it, and feel free to do the hands-on exercises along with the tutorial.
So I will talk about a specific method that's implemented in our toolbox. It's called the infinitesimal jackknife. It's a particular way to get the parametric uncertainties out through a cheap but fairly accurate approximation to the classical statistical procedure of jackknife. So let's assume that we are in the supervised learning setting. So we are given some data set D, and we have n data points. The covariates of the features are denoted by X here, and the responses of the labels are denoted by Y. And as a standard in the supervised learning problem, we're interested in learning the functional mapping from X to Y. We're going to assume that this functional mapping is parameterized by some set of parameters theta. So if you have a logistic regression model, these are the sets of weights of a logistic regression model, for example. Okay, so we know how to learn these models. It's fairly well understood. So we'll simply do some form of empirical, or if you have a regularizer, a regularized risk minimization. That is, we'll minimize this particular equation where the first term is basically just a summation over losses at every data point. So where I'm using the L sub n theta as a shorthand notation for the loss evaluated at the nth data point in this case. And R theta is just some regularizer, which is a function of the parameter theta. So given some data set, we can solve this minimization problem, and we end up with a optimal parameter theta hat. The one thing I do want to emphasize here is that this theta hat is a function of your model, obviously, but it's also a function of the data set. Right? Like if I had given you a slightly different data set, we would have solved the same minimization problem, but would have arrived at a slightly different theta hat. So fairly obvious stuff, but we'll make this explicit in our notation and express theta hat as a function of D, and D being the data set. Okay, so now we can ask about the uncertainty in the parameters stemming from having observed a data set D, a sample data set D from some population, but not having observed the entire population itself. In other words, if I observed a particular data set D, but how would my parameters have changed if I had observed a slightly different version of that data set D? So statisticians have worked on these problems for the longest time. And the math here is very well understood. So the standard way of dealing with this is to take your data set D and perturb this data set D many times in some way. And for each of these perturbed data set D, you'd refit the model, or you'd redo that minimization problem that I was talking about. So for instance, one way you could perturb these data sets would be by creating variants of the data sets where we're dropping out one data point at a time. So here D superscript 1 indicates the same data set as D, except that the first data point has been dropped out. So we go from X2, Y2 to Xn, Yn. I could repeat this and drop out the second data point and so on and so forth till I drop out the last data point. So this is a particular type of resampling scheme that is extremely, that is widely used. So procedures like the jackknife and even something like the leave one out cross-validation, which I'm sure everyone here is familiar with, basically employ this sort of resampling scheme. Now, once we have these S or N different resampled variants of the dataset, for each of them, we are going to fit our model. So do the minimization problem again. And then we'll get slightly different values of theta for each of these data sets. And these slightly different values of theta give us a sense of the spread of thetas, or a sense of uncertainty in the theta that arise from having only observed a sample rather than the entire population. So by looking at the spread, it gives you a notion of uncertainty. Okay, so this perturb and refit approach is widely used in practice, right? Like the jackknife, bootstrap, variants of cross-validation can all be thought of instances of this approach, where you're just changing the way you resample the data sets, the way you create the data sets, D superscript 1 through D superscript S. And then as long as we know how to fit our model to one data set, we basically doing this is procedurally trivial, right? Like I just have to fit this to my S different data sets. So this thing is procedurally trivial, but turns out that it is, since it requires S different fits, it can be computationally quite expensive, especially for large modern data sets where you have a lot of data points. This can be prohibitively expensive. So the infinitesimal jackknife, which I'll talk about right now, provides a fast approximation to the scheme. So instead of refitting, so you'll still create a bunch of resampled data sets, D1 through DS. But instead of refitting for each of these data sets, you'd refit the model exactly once on the original data set. So you'd refit the model to this guy, D. And then we can approximate, the approximation involves just a single matrix multiplication, what the parameter values would be at all of the other data sets, D1 through DS. However, before I can actually introduce what the IJ mechanism is, we need a little more machinery. So first, we'll consider a weighted version of our original learning problem. Notice that in the second equation right here, the only thing I've changed is now I have a weight, W sub n. Think of this as just a real scalar, a real number, which weights every data point specific loss function. And then we are going to solve this weighted optimization problem. And one thing to note now is that theta hat is a function of both the data set D, which I have not chosen to highlight here, but is also a function of W. So now it's fairly obvious if I set all my W sub n's equal to 1, or in other words, like if I use a vector, let's call n-dimensional vector W sub 1 of all ones, and solve the weighted optimization problem, I recover my original optimization problem, right? Because we're just multiplying all my loss functions with 1, so nothing has really changed. Okay. But more interestingly, if I set a particular coordinate of my weight vector, say the nth coordinate of my weight vector of all ones to 0, and solve the weighted optimization problem, that solution corresponds to solving the unweighted optimization problem where the nth data point has been dropped out. Again, this is fairly easy to see because if I set one of these W sub n's to 0, I'm just taking out the contribution that the nth data point made to my original optimization problem. So that's like fitting my original optimization problem with dropping that particular data point out. We can extend this reasoning. So instead of dropping out a single data point, we can imagine dropping out k data points. So that amounts to setting a bunch of zeros in this n-dimensional weight vector that I have. Where n, in case I didn't mention, capital N is the number of training points that you have. So this allows us to emulate things like k-fold cross-validation. And we can also think about making the weight vector itself random. And then if we draw this weight vector from an appropriate distribution, it allows us to emulate things like the bootstrap. So for the bootstrap, you have to draw it from a multinomial distribution, as it turns out. Okay, so we took our original learning problem, converted it into this weighted learning problem. The weighted learning problem allows us to express the parameters theta as a function of W. So now the key idea behind infinitesimal jackknife, which is going to allow us to move away from refitting the models, is basically a Taylor series expansion. The idea is that we can approximate the parameters theta at some arbitrary weight vector, which is close to the vector of all ones, by performing a Taylor series expansion around the vector of all ones. The first order Taylor series approximation is sometimes called the influence function or the infinitesimal jackknife. They have a couple of different names. And there are other higher order terms, obviously, in the Taylor series expansion. You can include these higher order terms. They come at the expense of more computation, but they give you increasingly more accurate approximations. And it is sometimes useful for certain kinds of perturbations like the bootstrap. To get anything out of these kinds of approximations, you would probably want the higher order terms. The toolbox currently only implements the first order Taylor expansion, which nonetheless is accurate and increasingly accurate with as n, where n is the number of training points, increases, and the delta W, the perturbation in the weight vector, is small. And it turns out that if you work out what this expression is, you end up with a term which looks like this, where theta hat W1 is the original fit. So this is having solved the original optimization problem on the entire training data set, you end up with a parameter, and that parameter is theta hat W1. And then you have a term which involves the Hessian of the model, and you have a term which involves the various gradients of the model. So you typically have the gradients of the model because we're typically doing gradient-based fitting. But the additional requirement is that we have this Hessian available. So we do need our models to be twice differentiable for this sort of approximation to hold. Okay. Okay, so now with the Taylor series expansion at hand, we can finally specify an algorithm which allows us to basically refit these models for free by approximating using the Taylor series approximation. So step one is fit your model once to the entire data set, right? So we had to do this anyway, but like we'll do it specifically for enabling this approximation to happen. Step two is to compute the Hessian of the model on the training set. This and invert it. The inversion of the Hessian in general takes cubic time in the number of parameters in the model, but if there's structure in your model, sometimes you can speed this up. But crucially, you have to do this only once. Now, perturb your data set a little bit. For each perturb data set, figure out what the appropriate weighting is, and these are typically easy to figure out. So for example, if you're doing jackknife, your appropriate weighting is just setting one coordinate of your data point to 0. And then use equation 1, this guy right here, to approximate what theta d sub s is. And finally, repeat steps 3 and 4 as often as necessary for each of your perturbed data sets. So crucially, the expensive bits, which is fitting the model and computing the inverse of the Hessian, need to be done only once. After that, you need to be able to evaluate this equation, and you can do this pretty easily. And it involves, really the bottleneck is one matrix multiplication. So this guy, which is a p by p vector, p being the number of parameters in your model, with a p by n matrix, where n is the number of data points. Interestingly, if you structure your weights in a way where only a few of the weight coordinates are changing from the vector of all ones, you don't even have to do this matrix multiplication. It turns out that you can just do a few matrix vector multiplications, and that's enough. All that to say that this can be done pretty efficiently. And that's the algorithm. So instead of doing S refits, which can be extremely expensive, we just do one refit and then do S matrix vector multiplications to approximate what the parameter values would be. There are also extensions to this work, which I won't have the time to get into, unfortunately, in this tutorial, which allow you to extend this to structured data and structured models. So instead of dropping out data points which are IID, which are independent of all other data points, you can actually drop out time steps from within a time series, or spatial sites from within a spatial extent. Okay, so without further ado, and in the interest of time, I'll just move on to the demo. But if you'd like to learn more about all the stuff that I quickly went over in this brief presentation, these are based on primarily on these two papers. One which came out in AI Stats a couple of years ago, and our NeurIPS paper from last year. Beyond the methods that I just talked about, they provide theory which allows you to bound the error in the approximation, so that these things, it'll tell you when these things are accurate and when they are not. And it also tells you that the error in the approximation, in the IJ approximation, grows smoothly with the error in the initial model set. This bit is kind of important because that allows you to use these sorts of approximations with stochastic gradient methods. So basically all of modern machine learning does SGD style fitting of these models. Turns out that there's theory which says that if you don't fit the initial model exactly, but use stochastic gradient methods, everything would roughly be fine. Okay, so next I'm going to move on to this demo. It's hosted in the repository under the examples folder. So if you'd like to follow along, this is the path to the IPython notebook that I'll go over. Okay, so again, the notebook is hosted in the examples folder under the Infinitesimal jackknife folder, and the one that I'm running here is demo infinitesimal jackknife.ipython notebook. Okay, so for this notebook, we are going to demo it on a simple logistic regression model. So in addition to importing various stuff that is required by the IJ or the infinitesimal jackknife approximation, we are going to go into utils and import a bunch of things which allow us which provide us the logistic regression functionality. So let me run that. Okay, and we need some data. We could have used whatever data we wanted. For this particular demo, I'm just going to use simulated data. So here, we are going to assume that the data has been generated by the following generative procedure. So the covariates are going to be 10-dimensional Gaussian distributed random variables drawn from a zero-mean Gaussian with isotropic covariance matrix. A sigma square for this particular example has been set to 4. I'm going to draw some weights at random, and then I'm going to draw the labels, so the responses, from a Bernoulli distribution parameterized by the sigmoid transform inner product between the weight and the data point x, right? This is all done in this helper function that we have, which is called synthetic LR data. It takes in 2 inputs, n. N is the number of training points, and D is the dimensionality of the data that's being generated. It produces 4 things: the covariates, the training responses, the test covariates, and the test responses. The number of test covariates, so the test data points that it generates, is 30% of this number. So it'll be 300 in this particular case. Again, this is just for illustration. You need to work with. Okay, so now that we have some data, let's go ahead and fit our logistic regression model. For this purpose, we have a utility function within the logistic regression class, .fit. And this function takes in 4 inputs. As you can imagine, the training data goes in, the training covariates and the training targets, along with an initial guess of what the parameters should be, and a weight vector. So I'm passing in the weight vector because this would make our life easier when dealing with the infinitesimal jackknife sort of approximation. So this weight vector is a vector of shape 1 and n, where n is the number of training inputs. So here I'm generating that weight vector right here. So this is going to be a vector of all ones, of shape 1 and 1 and n, where n is the number of training inputs again. So if this is a vector of all ones, then as you recall from the slides, you end up with the original minimization problem. So doing this fit is basically doing maximum likelihood estimation. What this function fit returns are the estimated parameters after having done this minimization. For the minimization, fit is internally just calling SciPy's minimize function. So that's either using BFGS or LBFGS, depending on whatever SciPy decides is appropriate for the problem at hand. And then once we have the parameters, we can ask what the accuracy on the test data set is. And so for that, we have a get test accuracy function. So again, fairly standard stuff. So let's just run that. So it did something, the optimization terminated successfully, and we end up with a test accuracy of 81%. Which is fine for a simple linear model. Again, the goal here is not to push accuracy numbers, but just to illustrate infinitesimal jackknife. Right, so with a reasonable model at hand, we can go ahead and do all the computations that are necessary for the infinitesimal jackknife approximation. So again, recall from the slides, we need two things, right? Like we need the Hessian of the model. So for that, we provide a utility function, compute Hessian. All of these, by the way, internally use autodiff tools, right? Like, so these are, if you wanted to do this for your own model and not our particular model, these functions extend to your model, so as long as you can auto-differentiate through the model. And we needed to compute the gradients. So these could have been stored while fitting the model, but I'm just going to assume that you did not store the gradients while fitting the model. So we are going to recompute them and package them into a Jacobian matrix, J. So for that, we have another function, compute Jacobian. These are just utility functions. And then finally, we can instantiate the infinitesimal jackknife object. It takes in the fit parameters. So parameters from the model having been fit to the entire training data set. The Jacobian matrix, the Hessian matrix, and a couple of configuration parameters, which are not particularly important. So I'm just going to skip over what those are. Okay, so let's run that. Since this was a fairly small problem, so n is 1,000 and our dimensionality is 10, computing the Hessian and inverting it does not take a lot of time. Okay, so now we have all the things that we needed to pre-compute available. So we had to do this sort of heavy lifting of fitting the model and computing and inverting the Hessian ones. All of that is done now. So now we can start messing around with our original data set and using the IJ approximation. We could do something arbitrary. So for illustration here, I've decided to drop out the 957th training data point. And our goal is to approximate the parameters having dropped out the 957th training data point. So if you're going to do this, remember, like, all we have to do is take a weight vector of all ones and set the 957th coordinate to be 0. So that's basically what I'm doing here. And then we can call the IJ, there's a function, there's a method in the IJ class, unfortunately also named IJ. In hindsight, we should have named it something more informative, which takes as its input this weight vector that I've just provided, that we have just created, and outputs the IJ approximation to what the parameters would be. And these parameters behave exactly the same as the parameters you get out of running the fit model using the fit procedure. So we can set the logistic regressions parameters to the IJ approximation, and then we can ask for predictions from the logistic regression model on the held out data. So since we had held out the 957th data point, it'll give you a prediction on the 957th data point using logistic regression.predict. So let's run this. And it does something. So it gives us the probability of class 1 as approximated by IJ is this value. So this value in itself does not mean anything. Hopefully this is accurate. So one thing that you might want to do next is to assess how accurate this approximation is. So there's some theory which tells us that increasing n, as in increasing the number of data points, and making small perturbations to the weight vector guarantees, provides certain bounds on the error in the IJ approximation. But we can also test it out empirically for a particular data set. So in particular, what you could imagine doing is leaving out a few data points and and exactly refitting your model and comparing the predictions made by the exact refitted models with the predictions made by the IG approximations. So that's basically what's happening in this cell. For for the sake of illustration, I've decided to pick the first 20 data points. We are going to leave each of these 20 data points one at a time and do both the IG approximation and the exact refit. Again, since this is a very small data set, both the exact refit is also fairly fast. So we can actually run this in real time and look at what happens. So this is a scatter plot of predictions on each of those 20 data points that we had left out. The x-axis is the predicted value under the exact approximation, and the y-axis for each of these red dots is the predicted value under the infinitesimal jackknife approximation. The closer this red dot is to the diagonal line, the better the match between IJ, the approximation, and the exact procedure. You can also quantitatively look at what the differences are in the predictions, and there are some differences, but these are fairly small. And again, like since things line up on the diagonal, we can kind of we can see that these things are very accurate. And again, as the number of data points increases, it's only going to get more accurate. So which is nice in a couple of different ways. One reason for you wanting to use this kind of approximation is when you have a lot of data points. Otherwise, maybe you could have just refit exactly. And it turns out that in specifically in that regime where you have a lot of data points, these approximations become increasingly accurate. All right, so now we run this approximation for a bunch of different perturbed variants of the data set, and then we can ask it to make predictions with each of those perturbed parameters that I got from having fed the perturbed data sets. And that's what this predict function would do. It'll give you the mean prediction and a lower bound and an upper bound. The interquartile range of this lower bound and upper bound are specified through the configuration parameters up here, which I'd skipped over a while back. So basically this alpha controls the, tells you what lower bound and upper bound to expect. So again, so we can run this and it'll give you results as you'd expect. So this guy in the middle is the mean prediction, and this is the lower bound and the upper bound from having done the infinitesimal jackknife approximation to the exact jackknife. So having left out one data point at a time for all the 1,000 training data points. And these are predictions from the test set, by the way. So I'm going to speed up a little bit in the interest of time. So again, as I was suggesting in my slides, there's no reason to just delete one data point. We could do this with more data points. So here I've picked 20 random indices to set to 0. So we could do that. And then we can approximate the parameters having left out these 20 data points. One note of caution here is that although this would be accurate, the farther away you move in the weight vector space from the vector of all ones, since we are doing a Taylor series approximation about the vector of all ones, you would expect our accuracy to go down. So if you make a lot of the coordinates 0, maybe you wouldn't get as accurate an approximation using IJ as you otherwise would have. And a quick note that we don't have to have these weights be binary, not just zeros and ones. We could downweight, upweight these weights arbitrarily, even have negative values. Everything mechanistically will go through. You'll be able to run this code. It'll produce some set of parameters. It's less clear what your how to interpret these parameters. Like having a negative weight, it's unclear what exactly you're approximating at that point. But you could do it if you have a good use case for it. And then finally, another plug, we can do these kinds of things for structured models. I wouldn't have the time to go into it in this tutorial, but if you're interested, check out this demo. Again, it's in the same folder as this particular notebook. It walks you through on how to do this for a hidden Markov model. So with that, I'll end. I'll provide a plug for my colleague Jiri, who's going to present next. So these infinitesimal jackknife style methods are interesting and they're useful, but they do ask a lot of you as a user. You need to have access to the model. Your model needs to be twice differentiable. You need access to the training data so that you can compute the Hessian. If you don't have access to any of those things, it becomes tricky, and it's not always clear how you would use these approximations. So Jiri, in his next bit of the talk, next bit of this tutorial, will talk about black box methods, which are very different from the stuff that we talked about, which allow you to do that when all you have access to are the inputs and outputs of your model, but not the model itself.
We thought we will spend the third to highlight a couple more methods that are featured in the UQ360 toolkit that are somewhat novel and very interesting also from the practical perspective. And these two things are, the first one is a method, which we refer to as meta modeling. And the second one is a metric that we believe is a very useful tool in the assessment of the quality of uncertainty quantification, in particular prediction intervals in regression. So I'm going to start with the first one, the meta modeling method. You may remember from Prasanna's presentation that when designing this toolkit, we set out with one major high-level categorization in mind, categorization of approaches. Most uncertainty quantification approaches can be classed into two bins, intrinsic and extrinsic. So while you heard that the intrinsic approaches are those that are based on models that actually have the capability of producing uncertainty quantification as a byproduct of their parametric structure and functions and whatnot, such as Bayesian models and Gaussian processes, ensembles, there are many, many examples in this class. The extrinsic approaches that you see listed here as a repeat are based on the idea that we have a pre-existing model that may or may not have the ability to produce uncertainty, and we do something on top of it. That's why they are also called post hoc, or they are actually referred to in the class structure in UQ360 as post hoc methods. I would like to pick one specific approach here that we again call meta modeling. The idea here is that you have a base model that is taking care of a task at hand, be it classification, regression, ranking, and whatnot, structural prediction. And now we have a secondary model that acts as an observer. It gets to see the inputs and the outputs of the base model, and it's trained to predict the success rate or failure rate, if you will, of the base model, okay? Now, there are several variants. In one simpler variant, the meta model here, the observer only gets to see the input and the output of the base model, which we refer to as black box setting. And in another variant, it actually gets access to the inner workings of the base, which might lead to an improved uncertainty prediction, and that is referred to as white box. Now, why do we feel strongly about, and by the way, I will be showing a quick demo of a particular setting of a black box meta model on a regression task. Now, we do feel very strongly about this, and that has several reasons. First and foremost, this is a very practical solution to many, many issues that developers, researchers are faced with in practice when deploying AI models. There are many cases where you are given a model that has been trained by someone else. Let's say you have a client's model to which you don't really have any reasonable access. You cannot retrain it. It may have been trained on large amounts of potentially proprietary data, but that model does not come with the ability to produce its own uncertainty. But we know that uncertainty quantification is basically a number one concern when we deploy AI models. And meta modeling is really the solution that offers itself, in particular in the black box setting here, where you can equip that model without needing any access to it. Besides that, there are also sort of related advantages there are many, so I just wanted to pick here one. that are based on the fact that you can teach the meta model to predict uncertainty or issues of the base model when you expose the base model to completely new conditions, for example, out of domain data, which is actually not necessarily possible at training time of the original base model. Another advantage we might actually mention is that meta modeling can capture both data and model uncertainty, or aleatoric and epistemic uncertainty. And finally, this method has been demonstrated to be effective. It is competitive to state-of-the-art, and was shown actually that in many settings it outperformed a series of competitive baselines. And I put some references here for you to follow if you're interested in further details. Now, in the toolkit per se, we have all of these meta modeling versions deriving from one abstraction, that is the post hoc UQ, which you will see if you have downloaded the toolkit. So you can either derive from there to implement your own meta modeling approach, but we also provide two main flexible classes, one for classification, one for regression, that I will demonstrate now. So let me see, before maybe going into the notebook, I just wanted to mention briefly what is the sort of high level interface. So at instantiation time, the user provides some kind of a specification of the base model and the meta model in terms of structure. What would you like to have there as a meta model primarily, but you can bring your own base model. And there are three possible ways of specifying this for each of these, for base and meta. One way is naming it, and I will show you an example of that. Another way is providing a class specification or class declaration rather. And the third way is to provide an actual pointer to an instance, to an existing instance. Once one of these classes is instantiated, there are two main public methods, fit and predict, with the obvious meanings. And this is, by the way, consistent with other modules in UQ360. Okay, so now I'm going to switch to my notebook. This example notebook exercises the regression, a regression task. There is another notebook for a classification task, and is stored in the folder black box meta model in UQ360 examples, black box meta model. Okay, so feel free to follow through with the steps that I will be doing. We are using a small regression task based on house price prediction, or involving house price prediction. And I'm going to show how easy it is to create a meta model given a base model, okay? So these steps are all obvious. The main line here is that we are importing the meta model regression class from UQ360. The rest is just collaterals. I'm then loading the Boston housing prices dataset, which is a relatively small dataset to play with. This is really just to show the process of creating such a model rather than focusing on performance. So the size of the data set is really not worrisome here. Now I'm doing the classic data science steps and splitting the data set into training and test. Here, just a quick scatter plot of how the problem looks like. There are multiple features in this data set, and the task is it's a regression task to predict a house price. We are now choosing only a single feature as a predictor, as a covariate, and that is the number of rooms in a house. You can see that there's a relatively good amount of correlation, so we are good to go. A small routine to display some results. Now, this notebook per se exercises all three instantiation methods that I meant, named, by declaration, or by instance. I'm going to just show quickly the first one by name. This is essentially a simple case, like you come and you say, hey, yeah, I don't even have a base model. I would like this class to actually create a base model for me to do the regression, as well as a meta model for me. Now, I can do that by simply relying on predefined names, which we have several of them in this class. GBR stands for gradient boosting regressor, that I now choose for the base model as well as the meta model. And as a user, I can also specify certain parameters that I feel strongly about. I do not have to do it. There will be some defaults there. That's really the simplest way of instantiating a meta model class. So now it's a named UQ model, that is the instance. Now I'm invoking the main public method, the first main public method fit, during which all the parameter fitting is done. So that is done now. And the second key method is predict. So now I'm providing to the, as you could see that during the fitting stage, I have both training and observations, or the actual ground truth here. I'm invoking the predict method with a batch of only the features. So that would be the number of rooms per samples. This method returns, just like other regression-related methods, returns the regression prediction, or the regressive prediction, the lower bound and the upper bound. And so I'm often referring to lower and upper bound as prediction interval. So that's just happened. Let's take a look at the result. You see in this chart in solid orange, the regression prediction points obviously are the test points and upper and lower bound. Okay. Now I'm going to skip the method of instantiating by declaration and go to the really the most interesting practical scenario where, like I said before, you have a model as an instance. That model might be of any type. It doesn't have to be sklearn model. It can be a client model. The only requirement that we place on that instance is that it has to be able to, it has to provide fit and predict methods, okay? So now I'm simulating that by creating another gradient boosting regressor here and calling it base model. So this would be this is the simulation of the case where, okay, this model is trained on thousands of hours of data or something like that. I'm also choosing to create an external instance of a meta model, which is in this case now a linear regression model, linear regressor with some configuration. Now the key is that I, as a user, can pass pointers to these instances into the meta model regression class. Okay, and I got that instance called UQ model again. I perform the fit and predict methods, okay, and can display the results here. So this is really a very simple walkthrough of the essential steps. That's really all there is to the very basic black box meta modeling. We have abstractions for white box meta modeling, and that give you the base classes for multiple variants. We also have a set of recent additions to the UQ360 that implement performance prediction and all kinds of interesting problems as instances of meta modeling. Just bring this to your attention as an interesting addition to the sort of toolbox, researcher's toolbox, something we call uncertainty characteristics curve. We believe that it's a very useful tool, but really good up to you to decide. There is it has an implementation in UQ360 accompanied by a notebook that goes actually into detail and walks you through all the functionality. I will just give you a gist of what this is about. So often, and I think Prasanna touched on it, often we are dealing with the question, how do we assess the quality of uncertainty? And in regression tasks, again, we are talking about prediction intervals, lower and upper bound. What you typically see is some kind of a notion of how well calibrated these prediction intervals are. Many papers, in fact, will give you the notion of calibration in terms of, okay, we trained it to be 95% coverage, And that's what happened on our held-out test set. But not much further information will be given. For example, were these intervals wide or narrow, or what was the mean bandwidth, the other metric. That is one type of problem that I see. The other type of problem is that people, when they do coverage probability, they decide on a certain level of confidence, for example, 0.95. Another work might actually decide on 0.9 or 0.99, and that makes the work kind of not necessarily not comparable, but hard to compare. So we now refer to this type of settings like 0.95 as an operating point. And we attempted to create a tool that is agnostic with respect to this operating point. That is what uncertainty characteristics curve is about. I have this very brief motivating example. Imagine you have model A and model B both generating prediction intervals around some regression. Okay, so you have the same case. Blue is regression prediction, orange is observation, and the gray or bluish area is prediction intervals around it. Now I might be tempted to say, well, I really prefer B because of the coverage probability. I miss only maybe 5% of points of my observations. This is the way to go. Now, of course, this is an artificial example. If you now rescale the scenario and scale up the output of algorithm A, you get a scenario where you get an outcome where you capture the observation really nicely. Again, this is an artificially nice example where you envelope all of the observations with minimal excess in bandwidth, okay? While if you scale down B's output that looked so good, you can see that there is really no signal in the shape of the prediction interval. It has nothing to do with the observation shape. So, and in fact, it was generated randomly. So it's really, if you think about it from this perspective, this would not be a good prediction interval. Now, I know this slide is busy, so I would like you to just concentrate on this bidimensional graph. At any point, with regression and prediction intervals, you will encounter two types of costs, or incur two types of costs. The first one is, loosely speaking, by overshooting the observation. That is what we refer to as band excess, but it can be also measured by absolute bandwidth of your prediction intervals. And at another point, we might undershoot and miss. So that is usually measured as the average miss rate, which is 1 minus coverage probability, or we have a metric that is more of a soft measure of that, which is a deficit in bandwidth. Okay. So now we have a bidimensional graph with two axes. On one axis is the type 1 cost, on the other axis type 2 cost. The UQ360 UCC implementation lets you as a user actually choose among multiple variants. You can choose what I called excess, or you can choose absolute bandwidth. You can choose miss rate and this band deficit. But overall, the idea is that we now have an axis system where we can see a trade-off. Now, how do we get that trade-off? We find a way to scale down or scale up, inflate or deflate, and the other way around, the bands of the prediction interval, so that we can actually start with a very thin sliver of a prediction interval around the regression prediction and inflate it all the way up so that it envelopes all of our observations within a certain batch of data. This is all based on a sample of data, such that our miss rate starts ranging from almost 100%. With that tiny sliver, we will be missing almost 100% of our observations and end up with a miss rate of 0 as we envelope all of the observations. So that gives rise to a set of operating points, or basically a curve. It's not dissimilar to the receiver operating characteristics curves. This curve gives us now deeper insight into the behavior of each model that generates prediction intervals. There are often seen in practice cases of crossovers of different models, meaning model A might actually perform better in a low misrate operating region, but model B might be the better one in a higher misrate region. So this tool gives you that insight. That's one outcome. The other one is we calculate the area under such a curve. That gives us a scalar summary metric of the performance of a prediction interval model that is what we say operating point agnostic. Imagine you do not necessarily know that you don't have an application in mind when you develop the algorithm, or you might have an application in mind, but you don't know what is the exact operating region. Are we focusing on 0.99 coverage probability, or is it more 0.8? So such a metric can give you an agnostic view and might serve a more general comparison. In UQ360, all the implementation is hides in this class, uncertain characteristics curve. There are many features, methods that are actually interesting, but there's no time to cover them. The area under the curve, we call it AUUCC, is also produced by a regression metrics, which is a class that will give you many UQ metrics in basically covering some of the metrics that Prasanna mentioned. So there you will see it as the area under the UCC. And finally, I would like to point you to the demo notebook, which really walks you through pretty much all of the functionality of UCC.
Okay, thanks everyone for listening. So that was the whole presentation. And can you guys hear me? Okay, okay. I see there are some questions.
Yeah, so there are some questions, Prasanna. Can you read the Q&A panel?
Oh yeah, let me do that.
Okay.
Okay, the first question, has the meta model uncertainty techniques in UQ360 been benchmarked on time series forecasting tasks? Yeah, so the benchmarks are not there in the toolkit, but I mean, that is one of our to-dos for future. But I just posted a paper on the chat, which was the original paper from which the meta modeling work has come out. So yeah, please feel to take a look at that. It's I think if I'm right, I think they're mostly classification tasks, and this is follow-up paper which I'll post in chat in a bit, which is on regression as well. And then there is recent work on performance prediction. So it's trying to not just estimate how good the a model is for per instance, but you're trying to like sort of predict the performance of the model and also have some sort of prediction interval around those performance metrics. So the regression one definitely has more details, but I think the one on sequential models, I think that might have some results on the time series forecasting, I believe. But it's not, the benchmark itself is not there in the toolkit yet. The second question is, any thoughts on whether and how UQ applies to unsupervised learning? Yeah, this is also quite interesting, and this is one of the other sort of future tasks that we have. And in unsupervised learning, if you take typical generative modeling, they do give you likelihood estimates, right? At least some models give you likelihood estimates. So, and we have seen in recent works that they may also be not well calibrated, as in they might either underestimate the likelihood, or they might be not really detecting, let's say, if you want to use it for outer distribution detection and so on, they seem to be still unreliable. So we don't have it in the toolkit yet, but it's also in the works. So we're trying to see if you have a model which has disentanglement properties and so on. So what properties of good generative model leads to good likelihood estimate? That's something that is interesting to look at. Okay, and to the second question. Oh yeah, okay. The paper I posted in chat.
Yeah, I don't think there are any further questions. But I think for the audience, it's important to know that the link and the presentations will be shared with the registered participants, and it will be available via the conference website soon after the meeting ends, probably. Right. So please keep an eye on the website. You'll get to know about the proceedings and also the link of all these tutorials, and all the information about the speakers are there in the website. Feel free to reach out to them. Think if there are no further questions, so probably we can call this a tutorial then. Yes, yeah, the recordings will be available. So it's again, so please keep an eye on the website, and the recording link will be shared with the registered participants. The full recordings will be available. Yes. If there are no further questions, maybe thank you, Prasanna, on behalf of all your colleagues who couldn't make it in person. So at least you played the recordings, so everything seamless. Thank you very much, and we call this the end of the session then.
Okay, yeah,
Very
thanks.
much. Thank
Yeah,
you.
thank you, and thanks everyone for joining.
Yeah. Bye.